symbolic systems.
Oh, sorry, yeah.
Neural symbolic systems, and what look like the most promising ways to work toward real AGI systems from where we are now in terms of understanding the mind and brain and available technologies. So I've been working on these sorts of ideas for a while, not as long as some people in the audience. Of course, the AI field goes back to the 50s by name, and even earlier by concept, with things like Norbert Wiener's cybernetics in the 40s. But I've been hacking with trying to build smart systems since the mid 90s, or back to the 80s, really, depending how you define it, and writing books and papers trying to mathematically and conceptually model how minds work since late 80s and early 90s. And I mean, there's a lot we don't understand still, but I would say there's been tremendous progress toward that time, both in practical achievements of AI systems and in understanding of how minds and brains work. The advances in practical achievements of AI systems and the advances in how minds and brain work have not always been aligned with each other, and that's an ongoing process, which is part of what I want to talk about here. What I'm gonna be able to touch on today is sort of an abstract of my way of thinking on these things. So I want to point people who are curious to go deeper to some reading materials. If you look in archive.org and just look for my name, Ben Goertzel, you'll find a bunch of relevant stuff. So there's a paper called The General Theory of General Intelligence, which is partly tongue-in-cheek as a title, but partly serious, and that surveys a whole bunch of work and thinking by myself and others, some of which is in the vein of what I'll talk about today. There's another paper on there where I talk about large language models and spend, I don't know, 90 pages or so trying to compare LLMs to what we know about how human minds work, and sort of look at what's missing there, which is a lot in spite of their quite impressive functionalities in some regards. And the specific practical AI project aimed at building artificial general intelligence I'm involved in now, the OpenCog Hyperon project. There's another review paper on there that goes over that, which has sections written by many of my collaborators on the project. So that's for those who want to dive deeper. But now let me just plunge right into it. So what is intelligence? Now, of course, what intelligence is an English word. It's a natural language concept, and natural language concepts are not necessarily scientifically the right concepts, nor are they necessarily going to be concrete and precisely defined, and that's not always a problem. Like, I mean, the field of biology doesn't have a crisp definition of life. It doesn't matter too much whether a virus or a retrovirus is given the label life, right? I mean, we know what's interesting are processes of reproduction, metabolism, movement, and self-organization, and so forth. And the label life is useful as a shorthand in casual conversation. Intelligence may be a bit like that. When you get serious, it devolves into a lot of other more precise properties.
Aqui. Por favor, me responde, tá bom? Eu aguardo o seu feedback e vou pedir então para o Jean-Pierre fazer a transferência para sua conta hoje ainda. tá? Ó, eu trouxe um short também para ver se dá em você.
Sorry,
Eu-
just a sec.
Tá muito grande para mim. Beijo.
Who usually helps me? Comment je supprime cette personne?
You go into the participants and the contributor that will help you.
Just a second. Is that the one who was doing it?
Yeah.
Oh, I should be up there. Yeah, deactivate the sign. Okay, sorry, excuse me, Ben, go ahead.
All right, yeah. My French is limited. I had trouble understanding what's going on, but yeah. So, nevertheless, there are some attempts to make the concept of intelligence more precise that are of some limited use in trying to understand both human intelligence and understanding how to build AI systems of various sorts. So one attempt to formalize the notion of general intelligence came from the field of algorithmic information theory and was summarized in the PhD thesis of a guy named Shane Legg, who had an interesting history. I mean, Shane worked for my first AI company, WebMind, in the late 90s. He then went on to do a PhD trying to mathematically formalize intelligence based on the idea he expressed to me many times in the late 90s and early aughts that at that time he felt the main obstacle to implementing a computer system that could think as well as people was not having like a well nailed down definition of what is intelligence. So he wanted to plunge into precisely defining intelligence. And I mean, my approach when he was working for me in the late 90s was, let's just build something really smart, and then we can worry about how to precisely characterize its smartness, afterwards based on doing experiments. He was like, no, we want to nail down exactly what the meaning of intelligence is, and that will tell us what to do. His PhD thesis, drawing on a bunch of work by Marcus Hutter, Ray Solomonoff, and others, made an attempt to do that. I mean, in essence, they tried to find universal intelligence as the ability to achieve arbitrary computable reward functions in arbitrary computable environments. And so you sort of average over all possible rewards in all possible environments, where possible means computable. And then you average how smart the system can be at doing that reward function in that environment. And how you average is sort of the crux of the matter. There's something called the Solomonoff prior, which weights reward functions in environments higher if they're more compactly described in a given programming language. So there's some fairly nice math there. I mean, if you compare this sort of characterization of general intelligence to the ways in which humans are intelligent, you quickly come to the conclusion humans are not that generally intelligent compared to these very rigorous mathematical criteria. When we think informally about general intelligence, we're thinking more like, okay, you've got Deep Blue that can only play chess. You've got, say, long ago, my friend James Albus had, automated driving systems for driving tanks and other UAVs in the U.S. military in D.C. So you've got something that drives a tank or plays chess is doing just that one thing. Now, compared to systems like that, humans appear to have the ability to take big speculative leaps beyond their programming, beyond what we were taught in school, beyond what seemed to have been wired in their brains by evolution. So in a certain informal sense, we seem better able to leap beyond our preparation than Deep Blue or than an army's automatic tank driving software. So in that sense, we seem to be fairly generally intelligent. We have an ability to generalize in a speculative an exploratory way beyond our experience. On the other hand, compared to this mathematical definition of universal intelligence, we're extremely stupid, right? Like it's very hard for us to run a maze in 3,912 dimensions, right? I mean, and no matter how hard we try, it's still going to be hard for us, just given the way that our brains work. We can't generalize our ability to run a 2D or 3D maze to thousands of dimensional mazes too well. I mean, we can if we can code a bot to run the maze, but there's a lot of limitations, right? I mean, we're not that good at doing math and science, even though we invented these things, right? So I mean, we're not even good at understanding, our own friends or family, for that matter. So we have a lot of limitations relative to a mathematically maximal general intelligence, which gives pause and makes one wonder whether this mathematically general approach tells you everything you need to know about what is human general intelligence. Because clearly there's a pragmatic distinction between a system that only drives a car and plays chess and a system that has the adaptability and flexibility of a human, even though both these systems are in a way really dumb compared to Legenhütter's definition of universal intelligence. And indeed, if you start to think about it just from a common sense psychology view, the idea that humans are optimizing one reward function isn't so much how we work. I mean, we can do that for a period of time. I mean, you can seek reproductive success. You can try to keep alive if you're starving or under threat. You can try to get good grades in school and make as much money as possible. But I mean, over the scope of a human life, we're really pursuing a whole variety of different goals. We're trying to entertain ourselves. We're trying to grow and learn things. We're seeking freedom in a way. We're just curious, right? I mean, there's a lot of different goals that pop up during our lives. And of course, part of development over one's lifespan is the ability to throw out one's old goals and not find rewarding what used to find rewarding, and originate new goals and be rewarded by new things. So it may be the whole paradigm of intelligent systems as reward maximizers is very limited, setting aside the fact that we're not maximally effective reward maximizers. So a more philosophical / biological view of general intelligence you could find in a book called Open-Ended Intelligence by a guy named Weaver, formerly named David Weinbaum, and he did a PhD on this at the Free University of Brussels. He's looking at intelligence as a sort of property of certain complex, self-organizing, adaptive, dynamical systems, and drawing on continental philosophy a bit, as well as biology, and just saying you have a complex, dynamical system which has a pattern of trying to individuate, to maintain itself and its boundaries as an integral system, and also trying to self-transcend, to grow beyond itself and adopt new forms and patterns that it didn't have before. When you have this dual aspect to a system, then you have an open-ended intelligence. And it's not that big a stretch to look at his individuation and self-transcendence and see, metabolism and reproduction in biological systems. And from this point of view, nailing down what is individuation or what is self-transcendence as a mathematical reward function is sort of beside the point. And he would say no formal characterization of these things will necessarily capture the whole concept. So sort of taking a cue from these and many other conceptualizations of intelligence, I early in my career started trying to formalize what is intelligence in terms of a mathematical theory of patterns. And it's all still prelude to trying to analyze human minds or build AGI systems. But I found that without having my head screwed on what I felt was the right way philosophically, I was lost in terms of trying to understand human minds or build practical AGI systems. So I was a big fan in the mid-1980s when I was a teenager of the American philosopher Charles Sanders Peirce. I mean, Peirce invented semiotics. He invented quantifier logic with for all and there exists and so forth. He had a metaphysical theory as well, which was based on a few fundamental categories, the main ones of which were called first, second, and third. Evidently, he's not a big innovator in naming things, but first was just like raw, unprocessed experience. Second is reaction, like the billiard ball, it's the other billiard ball. Third is relationship, where A connects B and C. And third is what gives you the whole web of patterns and relationships. So you could take this in the direction of consciousness theory and say, well, qualia are first, physical dynamics is second, and then, mind and cognition relationship are third. I mean, you can have fun adding more categories. You can go Zen Buddhist and add 0 for non-duality. You can get Jungian and add fourth for synergy and emergence and so on. But if you look at Peirce's category of third, what you can say you're getting relationships. You're getting A somehow stands for B and C together. And one insight Peirce had is that once you do that, you get everything else. Like you can build universal computation essentially, and you can build notions of simplicity and complexity as types of relationships. And I formalized the notion of pattern as basically simplification. Like F is a pattern in X if F can produce X, but F is simpler than X. And viewing a pattern as a mode of approximate simplification connects the notion of pattern with algorithmic information theory and a bunch of other math, which is about programs simplifying data. I don't want to go too deeply there now. That's done in some of the papers that I pointed to, but on a philosophical level, one is driven from this sort of philosophy to thinking of minds as systems for recognizing patterns in themselves and the world. And so this goes a little further than an open-ended intelligence. I mean, an open-ended intelligence is trying to individuate and self-transcend. But how can you do that? Well, to do that in a complex, ever-changing environment where there are risks involved, then you need to recognize patterns in the world and in yourself so that you can reliably individuate and self-transcend. These will include patterns regarding which processes you might carry out are likely to have what effects and what context. So being able to recognize patterns in yourself and the world will help you to achieve goals, but it doesn't mean there has to be like a fixed goal driving everything, right? And so minds may be associated with physical systems. A mind can be thought of as a fuzzy set of patterns in a physical system, and you conceiving intelligence in this way, you can do some math to show that a system for recognizing patterns in itself in the world, if it's good at recognizing a variety of patterns, it's going to be good at achieving a variety of complex goals in complex environments. So this way of thinking about the mind doesn't get you too far, but it leads to a particular way of thinking. Like if you're thinking about a particular kind of intelligent system, be it a human or an AGI, you start asking how are patterns represented in the system, what patterns are most conveniently represented in that system, can be most easily recognized and manipulated. What are the mechanisms for reflection and introspection that let the system recognize patterns in itself? So you're given a way of formalizing some obvious questions you might ask about any intelligent system, and you can then go a bit deeper. And some things I did in my earlier work is try to conceive things like evolution and autopoiesis, which is a system theoretic word for self-construction, how the systems can construct themselves. How do you try to view these things in terms of pattern dynamics? And evolution is then a general process where patterns that are successful in guiding a system or recognizing patterns in itself in the world, processes that are successful at this will tend to flourish within the system. Processes unsuccessful at that will tend not to flourish in the system. And this general notion of evolution covers things like Edelman's neural Darwinism or genetic algorithms and genetic programming. I mean, as well as classic neo-Darwinist biological evolution. Autopoiesis, or sort of self-reconstruction on the system, it means that if somehow a pattern that was useful for a system and recognizing patterns in itself in the world starts to fade in intensity, the system, there will be a causal dynamic whereby other patterns will sort of bring it back. So it's like self-repairing on the level of pattern dynamics. And these are very, very abstract general dynamics, but I'm spending precious time on them because I think they underlie the more particular dynamics that are traditionally identified as having a role in human-like cognition. You can also look at the structure of networks here. So you can look at patterns emerging from patterns, emerging from patterns, emerging from patterns. So you have deep networks of pattern emergence. And a cognitive scientist named Stellan Olsson a couple of decades ago wrote a book called Deep Learning, which was about learning in networks of hierarchical pattern systems, which is interesting to look at in the context of the current use of the term deep learning to describe a much narrower class of neural net systems. But the pattern of hierarchy as a mode of organization in a network is quite broad and important beyond any particular sort of biological or computational architecture. There's also a pattern of association or heterarchy where patterns spread some attention and resource to other patterns that they overlap with in some sense. And this underlay what Peirce called the one law of mind, the tendency to take habits. Tendency to take habits in Peircean philosophy basically means you have a hierarchical network of patterns that are connected by patterns with yet other patterns, and the resource allocation within the system to some extent follows this hierarchical network. And you can then see that these hierarchical and heterarchical sort of associational networks in the mind are often aligned with each other, which you could think of as a sort of dual network of hierarchical and heterarchical organization. And this broad organizational pattern is there inside transformer neural networks, which is part of why they have powers around LLMs and so on, but it can also be there in the knowledge graph of a symbolic logic system, as I'll describe in a few minutes. For example, these sort of abstract structural and dynamical patterns are not tied to any particular substrate or infrastructure. And then part of the reflection that allows the mind to recognize patterns in itself is that these hierarchical and hierarchical networks, these are patterns the system can to some extent recognize in itself as well, and then embody sort of approximate images of these network structures within the network structures, which is part of what brings us a self, which is something that current LLMs do not have, right? Like LLM or Llama 2 or Mixtral don't know who or what they are. They don't have a viable model of themselves, even though they can pretend that they do. And why that is, we'll talk about in a moment. So how would you go from these philosophical thoughts to something that you might sensibly call a general theory of general intelligence? Well, the thing is, if you view intelligence as being about finding patterns regarding what actions tend to achieve what goals in what situations, or as recognizing patterns in yourself and the world so as to individuate and self-transform, I mean, doing that in general is intractable in terms of computational or energetic resources. I mean, in the same way that achieving Legge and Hutter's universal intelligence in terms of optimizing, any computable reward function, any computable environment is intractable. So then to say something useful about general intelligence, either human or artificial, you need to specialize somehow. You need to think about, okay, well, what kind of environment is this system in? What kind of substrate is this system built out of? What goals and environments are we concerned with? My model of what a really general theory of general intelligence should look like is, if you feed the theory some knowledge of the motivations of a system, what it's built of, the environment it's in, what resources it needs, the resource constraints, this general theory should tell you what architecture will be good at surviving, flourishing, and growing, given all these motivations, environment, and constraints, right? And I mean, we don't have a theory like that. I could write down a theory like that in terms of category theory and other advanced math, but it's intractable to use in practice. But that's a way of thinking about general intelligence. When you think about human intelligence, you should think about, okay, we know what intelligence is in general in a philosophy sense. How does that manifest itself given the particular biological substrate and the particular set of environments that humans had? If you're building an AGI system, you ask, how does this general process of open-ended intelligence manifest itself given the hardware that we have, given the resource restrictions that we have, given the environments that we're placing the system in, given the things that we want the system to do? You then get more concrete, and you get to what I'd called in a paper in 2011 the embodied communication prior. I came to the conclusion many aspects of human intelligence originate from the requirement of trying to achieve goals in an environment where you're doing multimodal communication with other similarly embodied agents. So I mean, human intelligence evolved to control these sacks of meat in a world where there's other sacks of meat around, and you're trying to do stuff that will help you individuate and self-transform and survive, partly by trying to collaborate and communicate with these other sacks of meat in a shared environment. And you're doing this communication, by a variety of ways. You're doing it by making noises. You're doing it by waving your arms around. You're doing it by scratching pictures in the ground with a stick, right? So if you look at this as a thing for minds to do, this leads you to a lot of aspects of human-like general intelligence. And this is a long story that I try to tell in some of my publications, but I mean, you can look at the kinds of communication that we evolved to do, like language, making noises, and pointing at stuff, play acting and demonstrating and miming, depicting, like creating pictures or onomatopoeic sounds, or demonstrating what your goal is by doing part of the action. You can look at each of these kinds of communication that human minds have evolved to do, and you can tell what, to me, is a reasonably compelling story connecting these forms of communication with different types of memory that have been identified in cognitive psychology. And clearly our semantic memory for facts and beliefs is closely tied with linguistic communication, and procedural memory is closely tied with indicative and demonstrative communication. Sensory memory is closely tied with our ability to depict things, and our ability to remember goals and do constructive memory of goals is closely tied in with the ability to act out goal-oriented activity, which closely relates with mirror neuron networks and so forth. So if you look at the evolutionary pressures that were on us as we grew up as communicating entities, you can connect this by not incredibly solid, but quite plausible threads with different sorts of memory in the human mind. And works of, say, Michael Tomasello, to name one, of a variety of Stephen Mithin. So there's a variety of cognitive scientists who have told, so William Calvin, who've told similar stories. And if we go one step further, we can say each of these types of memory, which evolved in the human mind in order partly to deal with different aspects of multimodal embodied communication with similarities in the shared world. Each of these types of memory can be seen to correspond with different types of learning and reasoning, where I can think broadly about learning as newly identifying patterns in self in the world, and can broadly think about reasoning as, extrapolating from and combining already recognized patterns to form new candidate patterns that may be recognized in self in the world. So we have certain sorts of learning and reasoning that deal well with declarative knowledge, certain sorts that deal with procedural knowledge, certain sorts that deal well with sensory knowledge. And human brain seems to work this way, although admittedly that's a very coarse gloss of the incredible detail in cognitive neuroscience. And then when you start to think about AI systems, you can start to think about it the same way. Okay, how does my AI system do declarative memory? How does it do procedural memory? How does it do sensory memory? How does it do intentional memory? How does it do episodic memory? And how does it do learning and reasoning associated with each of these kinds of memory? You then arrive at a concept called cognitive synergy, which is a very obvious concept, which, however, has not been manifested adequately in the AI world historically. So if you look at good old-fashioned cognitive architecture, such as SOAR or ACT-R, which attempt to take the different kinds of memory, learning, and reasoning in the human mind and sort of mock up, simple, crude versions of these in a software system. One aspect of these is they're largely composed of a set of what you'd call black boxes, like your declarative memories over here in a box, procedure memories over here in a box. Whatever you do to learn declarative knowledge stays in that box. Whatever you do to learn procedural knowledge stays in that box, right? Now, the brain is not modularized in that way. And I mean, there was a book pointing this out called Beyond Modularity, whose author's name is slipping me at the moment, which would have been in the 80s or early 90s or something. The neural subnetworks that deal with learning procedural knowledge and the neural subnetworks that deal with learning declarative knowledge. I mean, they're largely interwoven in the brain. I mean, they're diffusing charge back and forth to each other. They're cooperating in ways that we have not yet very fully unraveled, right? And I think if you want to formalize this in computer science, what you would say is the learning and reasoning mechanisms associated with different types of memory stores can share intermediate state with each other so that they can guide each other in arriving at a conclusion, rather than just giving each other problems and getting answers. They're sharing intermediate state and helping each other to get answers. So this is what I call cognitive synergy. It's sharing of state and provision of guidance between learning and reasoning processes associated with different sorts of memory. And when you start to think about a human-like mind this way, it starts to suddenly get concrete in terms of AGI design. It doesn't constrain you that much. I mean, you could manifest different kinds of memory as different neural subarchitectures, or you can manifest different kinds of memory as computer science data structures that have nothing to do with formal neural networks. But either way, you're not making these distinct modules. You're making them able to help each other out of whatever bottlenecks or combinatorial explosions they may get their way into. So I had a paper some years ago formalizing this notion of cognitive synergy in terms of category theory with enriched categories, which you can find linked in the references I gave it at the beginning. So it's a precise enough notion, which is more helpful for building AGI systems and for modeling the brain at the moment, but it's not purely a hand wavy thing. Now, getting finally to AGI, the way I've been trying to manifest these ideas in my hands-on work with AGI systems has been not so neural net focused. Rather, I take as my basic data structure a large weighted labeled typed metagraph, where so a graph is a bunch of nodes and links connected to each other. A hypergraph is like a graph. You can have a link spanning multiple nodes. A metagraph goes further. You can have links pointing to links or links pointing to subgraphs. And that the nodes and links in my metagraph can have various quantitative weights on them. They can also have types associated with them, where a type can be represented itself by a subset of the metagraph. So you take this enriched weighted label type knowledge metagraph. This is a very flexible data structure. You try to do some fancy computer science and software implementation to implement this knowledge metagraph so you can manipulate it quickly on CPU and GPU and distribute it across a big computing network, which may be centralized or a decentralized computing network running on a blockchain. So there's a bunch of plumbing in dealing with this knowledge metagraph. But then you can represent declarative knowledge, you can represent procedural knowledge, you can represent sensory motor knowledge. It's a very general sort of meta-representational fabric. And then if you've put your learning and reasoning algorithms in this same knowledge metagraph, because you can implement programs inside the metagraph also. So if you put the programs embodying learning and reasoning on these different types of knowledge in this same metagraph, then you have a very natural framework for allowing cognitive synergy to manifest itself, because your learning and reasoning algorithms and your knowledge of different sorts, they're all in this same graph framework. And that's the approach I've been playing with for 2.5 decades now, or something, in a succession of different software systems. And of course, you could say, if you've been banging on this so long and haven't got a human level thinking machine yet, maybe it's the wrong direction. On the other hand, in the 90s, I was teaching multi-layer perceptrons, and it took 3 hours to use backpropagation to train a neural net with 30 neurons, right? So, of course, backprop was invented in the late 50s, early 60s or something. So we've seen in the recent history of AI that fairly old ideas with modest but not huge improvements and emendations, when deployed at tremendously greater scale, have yielded tremendously better results, right? And so my bet is that the same will hold true for this sort of AI paradigm, that this approach where you implement many kinds of memory learning and reasoning in a common knowledge metagraph and let it roll to synergetically self-modify, recognizing patterns in itself and its environment. My bet is we're going to hit pay dirt with this over the next few years as we deploy it at very large scale, similar to how deep neural nets started to do so much more when they were deployed at very large scale. And there's just a lot of particularity in math theory underlying all this that can't be gone into in a brief talk like this, though. So, I mean, as just one example, so you have declarative knowledge, which is facts and beliefs. You have procedural knowledge, which is basically programs for doing things. Well, there's a whole school of knowledge in computer science to do with Curry-Howard correspondences that tells you how to map logics into programming languages, right? So there's a bunch of math for mapping declarative logical knowledge into procedural programmatic knowledge, and this helps with the cognitive synergy to map declarative into procedural learning and reasoning, right? So there's a lot of story underlying how do you interoperate between these different types of knowledge and associated learning and reasoning mechanisms. Now, if you look at this at language in particular, you can try to cash this out in terms of category theory, using category theoretic models of the metagraph. And you can articulate one category theory called morphisms between linguistic representations like parse trees or semantic graphs, logical representations with the quantifier bindings and such, perceptual representations in terms of the tree structures you can induce from images or sounds, action representations in terms of structured models of procedures. And this I want to just briefly mention because it's a way of thinking about symbol grounding. I mean, you can think about symbol grounding in the crudest way as constructing enriched category theoretic morphisms between linguistic structures and perceptual and action structures. And that's I mean, of course, the simple mapping of like the word cup into the perceptual cluster for percepts of cups. I mean, this is an example of that, but not especially the most interesting example of that, right? What's more interesting is grounding more abstract linguistic patterns and more abstract perceptual or action patterns, and morphisms and enriched categories gives you a way to formalize and think about that. And we can talk about that more in the discussion if that interests someone. So I tried to lay out a fairly detailed design for how to build an AGI system based on all these ideas in a 2-volume book from 2014 called Engineering General Intelligence. You know, I've now been going through a process of revisiting all that and modernizing it in the context of a new AI system we're building called OpenCog Hyperon. I mean, you could, at a very, very high level, this is borrowed from Aaron Sloman, the cognitive scientist who's been at it even longer than me, based in UK. I mean, so you can look at a basic flow chart like this for driving a human-like mind, and where you have a system perceiving, which is the left, acting in an environment, which is action is in the right. It's using a long-term memory, working memory, it has certain motivations, deliberating, it's metacognizing. But then the real voodoo goes into, okay, I've partitioned off the long-term memory into declarative, procedural, sensory, blah, blah, and identified different learning and reasoning mechanisms associated with each of those types of memory. And then there's a certain synergy there between those. So at the level of a high-level architecture diagram like this might as well be SOAR or something. But the magic really is supposed to be in the synergy between the different algorithms doing learning and reasoning on different sorts of memory. Now, I created a software system aimed at manifesting all this in 2008 called OpenCog, and we had some open source community for it. The last 2 years, we've been rebuilding that from the ground up as a new code base called OpenCog Hyperon, so a new OpenCog version. And the atom space that you see there is local atom space and distributed atom space. The atom space is the weighted labeled metagraph, where we call nodes and links in the metagraph atoms. And then when you see at the left, we have probabilistic logic, program learning. Well, probabilistic logic is about declarative knowledge. Program learning is about procedural knowledge, and so forth. Now, building a practical system like this in the modern era, you have some confusing facts to deal with, one of which is some deep neural nets, which are not built according to all this framework, do some amazing stuff. And so I'm sort of taking a pragmatic / idealist perspective. I mean, over the next few years, I would like to re-implement things analogous to CNNs and transformers within the OpenCog Hyperon knowledge metagraph. And I think that will get you better synergy between the processes these things do and other cognitive processes. On the other hand, right now, I mean, we can interface our OpenCog system with Torch, which runs lots of big neural networks. We can represent layers of a neural net in Torch, in the Torch compute graph. We can map them into nodes and links in our knowledge metagraph, right? So we can synergize external deep neural nets with symbolic and evolutionary stuff running in OpenCog, and the software interoperation works fine. The thing is, you can only go so deep in terms of cognitive synergy, not so much because these neural nets are running in an external library, but because they're just not instrumented to take feedback into their learning and reasoning process from external sources. But in any case, OpenCog Hyperon, I linked a paper on that. There's another paper on Meta, which is the custom programming language we've created to create procedural knowledge within this knowledge metagraph. So procedural knowledge in the metagraph, we also made a textual form for, which looks like a programming language, which is called Meta, METTA, Meta Type Talk. And there's, for those of you who are developers, there's a code base on GitHub. You can plunge into some of the code experiments that we're running now. It's in the true AGI-IO GitHub repo, Hyperon experimental sub repository. And now I think I'm out of time. I'm going to take 30 seconds more to to mention some exploration I've been doing in how all this mess deals with the AI ethics and sort of aligning AI ethics with human ethics, which has been a buzzy topic lately. There's a paper I'll point you to just about LLMs showing that GPT-4 can, which I wrote with my son and one of my colleagues, but this basically we showed that GPT-4 can predict what humans will say is ethical, given a textual description of a situation as well as people can, which is interesting because human ethics is a very complex and voodoo-like thing. But apparently LLMs have enough knowledge to predict what humans will say is ethical perfectly well. However, that's very, very different than being ethical agents. And if you go back to the theory of open-ended intelligence, you could articulate like what do we really want an AGI system to really be a moral and ethical agent, which has to do with compassion, empathy, and reflection on your own self and understanding of your own processes. And you can tell a story about how all these things can be manifested in an OpenCog type system. I don't know a story about how these things could be manifested in a large language model, for example. But anyway, as with all the other details of what I've talked about, I'll send those who are interested to look up the references. But I hope I've at least been able to give you a sort of a high level abstract or intellectual freak show, or however we want to characterize it, but sort of what are the significant points of at least things I've been looking at and trying to do.
Okay, thank you very much, Ben. The questions will start to flow. Usually it requires a little bit of unplugging to get them to flow. And I'm the one that takes the role of the unplugger. So I liked when in the beginning you said that when you're giving no nonsense talk, you said, well, basically, what is intelligence? What is general intelligence? Well, we use the word smart, and you sort of suggested that it might be something along those lines that we should be thinking. And I thought that was fine, but I lost the thread of it. And we went on. I mean, what is a universal general theory of smartness? What could that be? Could it be, could there be anything? Could there be just one more sentence? Could it? Could we have a general theory of movement of movement of what? Whom? Where?
Well, I mean, Newton's law of motion attempted to be a general theory of movement, right? Which is then upgraded by quantum mechanics and general relativity. So in a way, these are general theories of movement, which are precisely what you appeal to when you solve the Lagrangians to figure out how a robot arm will move, right? So if you look in the physics example, we do have a general theory of movement. We then have a decent mathematical theory of movement of multi-jointed arms as well. And there's books on reaching and grasping and the mathematics there, and how the Lagrangians for reaching and grasping, tell you what to do when building neural models of robot arms. So there we have a general theory of movement. Then we have a more special theory of movement of multi-jointed arms, right? And I think the analogy there is decent. I mean, I think we have a very general notion of what intelligence is, or really an assemblage of them. I mean, one is Legenhutter's, maximizing computable rewards in computable environments. One is, Weaver's complex self-organizing system pursuing individuation and self-transcendence. So you can have the Peircean thing of recognizing patterns in yourself and the environment. And you can formalize all these. They're kind of useful, but they don't tell you much about how to build a particular system. So then once you have some constraints, that's when things get more interesting, right? So you have a constraint.
I'm afraid I have to cut you off because questions are coming and I'm not entitled to this long an answer. We have
Well,
Anne-Marie who has a question. Chris has a question.
Well, give me 20 more seconds though. So
Okay,
I
20
mean,
seconds you can have.
once you have a constraint, you know what kind of system you want to program or build your system in, what kinds of things you want it to do, right? Then given these constraints, you have to say, how do these very general notions of intelligence, how do they manifest themselves within these constraints? And what I think a general theory of general intelligence should be is something that tells you how you map the very abstract notion of intelligence into a real system conditioned on a certain set of constraints. And I mean, and then all of human cognitive science is viewed as how do you take the general notion of intelligence and figure out how it operates conditioned on the constraints of the human brain and the human evolutionary conditioning.
Okay, thanks, Ben. And now Anne-Marie, not too long.
Yes, I promise. Okay, thank you so much for this presentation. It's really interesting. I want to ask about the focus on patterns in trying to define general intelligence instead of, not on what generates the pattern, right? If you think of language as part of intelligence, sometimes you use language, most of the times, to express thoughts, but maybe the thoughts, are not perceived in the same way that motion is perceived and things like that. Thoughts are objects of the mind, right? And then something happens such that they become understandable, all things being equal, by humans or by computers, right? So this is one aspect that I want to talk to you about. What about what generates patterns? For example, in language, then again, the question is language represented as patterns of sequences of words, where there's more abstract than that? And we know that in some theories, they're oriented graphs. Now they start reintroducing those in transformers at later stage, but basically, why is general intelligence recognizing pattern and organizing this pattern in networks, and not why we want to explain why this pattern exists? And then that's my question. I have more, but that's all I would ask.
Hold them. Go ahead, Ben.
I think that the math is clearer than the words here, because I mean a pattern, as I formalized it, is a process. I mean,
yeah.
F is a pattern in X if F is a process that produces
Yes.
X and is judged as simpler by some reference observer. So I mean, when you're looking at language, you could look at patterns in sequences of words, or you could look at the habitual processes in the brain that produce those sequences of words. And I mean, those are also patterns, right? They're just, are you looking at patterns in temporal patterns of behavior in the dynamical system, or are you looking at patterns in the product, which is a bunch of sequences of characters or sounds? And I mean, you could both are interesting and both are necessary to look at. I mean, you also touched on causality there, on which processes cause which patterns, which is a whole other kettle of fish, certainly. But
Yes.
I answered your first question.
Thank you. More maybe email. Thank you.
Okay, Chris, you're next, but before you, there's someone here who wants to ask a question from here in the room. Tu veux que je traduise ou tu peux dire? Vas-y.
Yes, hi. So, first of all, a great presentation. I actually had the opportunity to read your book some years ago, The Patternist Philosophy of Mind. Great book. So doing my doctoral mostly on the intersection between quantum computing and artificial intelligence. You do touch on quantum mechanics in your book, but it was written some years ago. So I was curious, in light of the current the advancements with large language models, what do you think the role of quantum computing could be in achieving general artificial intelligence?
I mean, to me, LLMs are off to the side of that, because I mean, I don't think LLMs are AGIs at the human level. I don't think LLMs are ever going to be able to generalize and sort of leap beyond their training data in a very dramatic way. I mean, I think they're very broad because their training data is so broad, but they don't jump so far beyond their data. And I mean, that would be true of an LLM if it were implemented on a quantum computer or a Penrosian quantum gravity microtubule supercomputer or whatever. That's just about the architecture of transformers. They don't embody abstraction, which is necessary for generalization according to all sorts of learning theory. But I mean, if we go to quantum mechanics, I mean, I think quantum computing becoming more of a real thing is exciting. Nothing in the practical engineering advance of quantum computing technology has yet changed my thinking about quantum computing and AI. I mean, my own take is quantum computers will be amazing, and implementing AI on them will be great, and will probably be part of how we get beyond human level AGI to massively super intelligent machines. I doubt that we need quantum computers to implement human level AGI, partly because from all the neuroscience I've seen, the macroscopic quantum effects in the brain, while existent, are not really the main thing underlying how we do cognition. So I mean I think we could be modeled as classical computers close enough, which makes me think digital computers are probably enough for human level general intelligence. But I mean,
That sounds like an answer.
Once I can plug a QPU into my laptop, I will do it. No, yeah.
Now, next question is coming from Chris Dort. Go ahead.
Yes, thank you very much. I also would like to connect to the patternist theory of mind, because I really like that. I really like your idea that we need to look at patterns. On the one hand, for philosophical reasons, philosophers have been too busy with structures, like universal structures, and haven't paid enough attention to patterns which are more local. But also because when I speak to computer scientists, they always say, yes, there are patterns at work in large language models or in other computational systems, statistical systems. So patterns are really important, and I think you're doing a great job pointing that out. And I also think, yeah, the patternist theory is important. I just wonder, are there different kinds of patterns possibly? Like computers, they're dealing with statistical patterns, of course. Humans are usually rather bad in dealing with statistics, and at least on a large scale. And then there are other patterns in the human mind, and or maybe other patterns. And I wonder if that might be important to go beyond this mistake you pointed out in the beginning of defining intelligence as like just one kind of thing. Because if you think of patterns as mathematical patterns, then they're basically one kind of thing. But you could also think of patterns of perception, for instance, that those have been discussed in Gestalt psychology. And maybe those would be interesting to look at. So I would like to get your stance on that.
I mean, from a pragmatic view, as someone building AI systems, I would recourse to the Church-Turing thesis here, I guess. I mean, the formalization of the notion of pattern using algorithmic information theory is like, I mean, you have a process that generates some entity, and the process is simpler than that entity by some assumed simplicity measure. And I mean, if you want to go postmodern, you say, well, simplicity is associated with some observer. It's not objective. Then you ask, what language is the process implemented in? But if you take a computing theory approach and say that process is a program implemented on some universal computer, I mean, then you could say, with the Turing thesis, like any universal computer will simulate any other one, right? So as long as you're within that domain of things that are in principle computable, there will be many different kinds of patterns. Some patterns will look simpler on some sort of reference universal computers than others, and this is very important in practice, of course, because the patterns that the human mind can recognize within a certain amount of resource are different than the patterns that some AI system would recognize within a certain amount of resource. But yet you can map the two into each other using standard computer science ideas. Now, not everyone buys that. Like if you talk to Selmer Brings-Jordan, another cognitive scientist, he thinks the human mind relies on hypercomputing that goes beyond the Turing complete computers. And in that case, he thinks the human mind is recognizing some kind of pattern that is not equivalent to what a digital or quantum computer could do. I'm a bit skeptical of that one, but I mean, conceptually, it's a well-formed notion.
Okay, thank you.
Thank you.
Anna Kim, it's you.
Thank you. I go very short. I just want to know, what do you think can be considered as the primary source of weaknesses in the AGI? Is it related to the volume of or the type of training data, the design of the systems, or maybe our understanding of certain cognitive mechanisms, or maybe something else?
I mean, we don't have human level AGI systems yet, so we don't know what their weaknesses will be. But I would say the weaknesses I see in the tools and infrastructure that we're using to try to build human level AGI, it's really the rigidity of the tools that we're using. I mean, the human body is made of these organs, which are like life forms in themselves almost, which are made of these cells, and each cell is such a complex living thing, right? So, and the cells have little, the nucleus is its own complex living thing, right? So, I mean, we have levels and levels of living, adaptive, complex, self-organizing, responsive systems inside us. And so when we do something like eye-hand coordination, I mean, you got muscles that are adapting. The cells in the muscles are manifesting their own sort of intelligence there, right? So when the engineering technology that we're using, the underlying components are much more rigid. They don't adapt. They don't learn like cells do, right? So that, I mean, that it gives greater reliability in a sense, and durability, and it means you can swap out broken parts for new parts and so forth. On the other hand, it sort of means you've got to explicitly do a lot of things that sort of happen implicitly because of the living responsiveness of the lower layers in biological systems. So that's that seems like the biggest weakness.
Very good. Okay, I think we've had another answer, and now allez-y. Vas-y, allez-y.
Yeah, thank you. Thank you. All those are the meta representation in OpenCog Hyperon resolve conflicts between different cognitive models like neural, symbolic, and evolutionary system. Or we resolve or handle those conflicts if they are.
First of all, I'd say just because you have AI algorithms coming from different paradigms, following different dynamics, they don't have to have conflict. Sometimes you can just map one into each other, right? So I mean, you could do program learning on programs, you can do logical reasoning on logic expressions, and you can articulate a precise morphism from programs to logic expressions, and there's not a conflict. It's just that some things are more concise and efficient at one end of the morphism than the other. But the other half of my answer to your question will be, when there are conflicts, which could be from two different types of learning process, or it could be just two different trains of logical reasoning leading to different conclusions based on different evidence sets or something. When you do have a conflict, we don't necessarily try to resolve that conflict. I mean, we are not trying to make the OpenCog atom space embody an entirely consistent and coherent model of the world. And I don't think that I myself have a completely consistent and coherent model of the world. I mean, more on some days than others, right? But I don't think that's how humans really work. So, I mean, I think sometimes you have to just let inconsistent things exist in your knowledge base, and you don't have to reconcile them. And I mean, you can get fancy about this. You can do pair-consistent logic, which I've had some papers on. So you can do logical reasoning using axiom systems that allows the inconsistency to stay there without it being explosive and making everything nonsense. Or you can very simply just, if you have two conflicting things, sometimes you focus attention on one, sometimes you focus attention on the other, which is a lot of what people do in such cases, I think. So you don't, that this is a big difference between the approaches to probabilistic reasoning. I'm taking an OpenCog and things like Bayes nets or Markov logic networks. A Bayes net or a Markov logic network tries to have a consistent probabilistic model of the world over the whole network, and we don't try to do that.
Okay, that sounds like an answer.
you.
And as I promised to Anne-Marie, you have a second crack at it now, if you're still there. Anne-Marie de Chuyot, are you there?
No, she gave up on us.
It looks like she's gone away. Okay, we have a little bit of time left. Are there any? Okay, yes, go ahead, Chris.
So yeah, coming back to Anne-Marie's and my question with regard to like different patterns. So what I thought of with patterns we recognize, with perceptive patterns, is that we something comes to our mind as a pattern, as something that we recognize as a whole. Right? We don't recognize the different parts. I mean, maybe it's implicit in our recognition of a pattern, but really we see the whole thing. We see like the check pattern in my scarf, and it comes out if we pay attention to it. And that kind of pattern has been called a Gestalt in earlier psychology. And it seems to be something holistic that is not the same as a computational pattern where we have relations between items, and these relations we can define in mathematical terms. But here there's something, patterns in our perception. And I think, I mean, patterns are all over. Whenever we recognize something, whenever we see things as a thing, we have this holistic appearance of there to be something. So the question would be, do you think we can define these then in mathematical terms?
Yeah, no, this is a fun one because it lets us go back to the philosophical foundations. So Peirce had first, second, and third, and then if you go into Carl Jung, the psychologist / philosopher, I mean, he viewed those as just the first few of the numerical archetypes, right? And Jung's archetype for number 4 was basically emergence and synody. He'd do a bunch of mandalas to symbolize what he called fourth. And this was this was really about Gestalt. It's about how different thirds, different relationships sort of interlock to give some emergent structure, right? And this is what is symbolized in mandalas. And you can, I tried to formalize this in my first book, The Structure of Intelligence, in 92, is what I called a network of emergence. Like you could have three things where this pattern emerges, like A emerges from the combination of B and C, B emerges from the combination of A and C, C emerges from the combination of A and B, right? So then you can look at a network of mutual emergence, and you can analyze mandala patterns that way. And I implemented a measure of this once to try to measure the aesthetic quality of a piece of music, because I was using genetic algorithms to generate music, and you want to know what sounds good. And apart from music theory things, actually having this sort of mutual emergence between either explicitly different voices or implicitly different passages over time is an interesting indicator of aesthetic quality. So I think of a piece of music. So I think you can formalize this sort of thing. It does bring you away rapidly from the domain where there's too much useful math or computer science. Like there's you can formalize it, but there are not many tools to say much about it when you get there, right? Which is and you start to hit irritating limitations of category theory, which is one of my favorite tools, because I mean category theory, it's all about arrows, so you're following an arrow from one place to another, but it's in a way very sequential and linear, just like a formalization like lambda calculus is very linear. It's written as a string with nesting of quantifiers, and you want a kind of math that's more network based, right? So you have things like pi calculus and row calculus, which are like network lambda calculus. There's something called a pictoverse, which is like a category where the arrows play off in all directions, right? So, but we're just grasping barely to have the math to say anything useful about this sort of emergent, coherent, like a mandalic fourth, as Jung would have called it. But you can go there. But it's frustrating sometimes how you end up putting more effort on the directions where there's more tools rather than the directions that are more sort of conceptually and philosophically promising. And this is an area where just not that many tools.
Okay, Allez-y has a
thank you.
second question. Tu as une question?
Yes.
Okay, go ahead, allez-y, et puis ensuite il y a quelqu'un ici.
Thank you. I would like to know what specific methods are you using to evaluate the improvement in language understanding of AGI system when embodied in robots compared to embodied system. What specific method are you using to improve it?
I mean, I think evaluating a specific function like language understanding on its own is quite difficult, actually. I mean, what's done in natural language field to evaluate language understanding is mostly question answering, right? So I mean, you have corpora of questions and answers, and you evaluate what % of the time does it give what we consider as the right answer. And if you want to do that with robotics, it's not too hard to see how to do that. I mean, you have a robot in a certain environment, and you can pose questions and answers about the environment. Let the robot explore the environment and see the environment and do things, and then ask a question. See how often does it give the correct answer, right? So I mean that's a perfectly reasonable way to evaluate language understanding in an embodied system. How to evaluate general intelligence in this sort of system is much, much harder, right? Because you could see, like, to answer common sense questions about, you know, what's in this room I'm sitting in right now. Okay, if you train a system with video from millions of rooms like this in different houses around the world, I mean, perhaps some conglomeration of deep neural nets with very little ability to generalize, or very little of what I would think of as fundamental understanding, maybe it could answer questions about this very well, and it could do symbol grounding very well, right? So, like, I mean, if you show it something this with like a cup inside a cup, I mean, if it's seen a lot of cups, a lot of things inside other things, sure, it could ground, you know, the phrase "cup inside a cup" in this image that it's seeing, right? So I think, so just answering the question, like, is the transparent cup inside the cup with a picture on it, or vice versa? That's evaluating language understanding in the embodied context. I mean, evaluating general intelligence is not the question you asked, but to me is a more interesting question. Is much harder, right? Like, when I think about that in the domain of computer music that I've worked in a lot, like, we have neural net models for music now. I can generate a 12-bar blues song quite well. I can even generate a cool guitar solo for some weird rhythm that I made up. But if you, on the other hand, if you took deep neural nets and trained them only on music up to the year 1900, they will never invent neoclassical metal, you know, hip hop or progressive jazz, right? So there clearly were leaps that human culture took that are beyond the extrapolation that current neural models can do. But how to pin that down precisely is a little thorny, given that, I mean, humans are still, we're short of, like, Marcus Hutter's idea of optimizing computable functions in computable environments. We can, like, I can't effectively compose a piece of music with 500 independent voices and coherence among all of them. I could write a script to do it, but I couldn't do it in my own mind. So, like, how to capture the ways in which we're clearly way more generally intelligent than current LLMs, yet we still fall short of, like, ultimate mathematical general intelligence. This is a dodgy thing to measure and quantify, yet very qualitatively clear, right? So that's an interesting research area.
Okay, thank you. Now we have a question from here, Iris.
Yeah.
Wow.
Hi. Yeah, my question is, well, a bit of context before. I've heard about there's a quote what's called active inference, and I'm not an expert in the field, but I've heard what was
Iris, lentement, il va pas comprendre. Et fort.
All right. Yes, so I have heard about additive inference. That's an approach that, and I'm not an expert, but it sounded interesting in a way that it's a way basically that we perceive in a way to minimize the surprise of our perception. And I was wondering if you consider that links between this and the patternist approach in a theory of general intelligence.
Did you get the question?
Yeah, she's asking about the active inference approach, which is oh, what is, I'm stupidly blocking on the guy's name, although I should know it quite well. But I mean, there's a particular note.
He spoke in this series too.
Yeah, I know, I know him. I know his work quite well, but I know, and my friend Alex Arorbia, who is at RIT, he's actually implementing some computer science inspired by this stuff, where he has an approach that does learning in neural networks using predictive coding rather than using backpropagation, which is could be interesting. It's more localized and seems a big step beyond Yoshua Bengio's difference target propagation, which is another way to localize learning in neural nets. But yeah, my impression of the active inference approach is,
Carl Friston.
I mean, Yeah, that's it, Friston. Yeah. I kept confusing it with Carl Pribram, who was another old neuroscientist friend of mine, so I was blocking it in my mind. But Carl Pribram has passed away a while ago. Friston is still doing great stuff. You know, I can't evaluate that as neuroscience too well because I'm not a neuroscientist. I would say from a math and computer science view, I haven't seen much that's helped me there. I mean, the idea that we're trying to minimize the Kullback-Leibler divergence between our model and the perception. I mean, true, but I mean, we all know that we're trying to construct generative models that will approximate what we see. Like I don't need Friston's active inference to tell me that's been obvious for a long time. And when I look at how Friston tried to model action, it sort of seemed like a hack. It seemed like we're trying to learn an action procedure so that, you know, the outcome of our action procedure has a small Kullback-Leibler divergence with what we would observe if we saw the action or something. So when I project that theory into the AI algorithm domain, I never saw anything that didn't seem trivial to me. On the other hand, Alex Arorbia's work made me a little more optimistic because he has a cool new way of training deep neural networks, which is inspired by Friston's work and which seems to have some real advantages to back propagation. And then that seemed quite interesting. Like Aurobia, he's error propagating, but there are specific neurons in the network that embody the error. So you can do sort of error propagation with a fully localized way without requiring any sort of global consistency or global process, right? So I mean, if Friston's work inspires Aurobia and others to develop cool new algorithms in that conceptual space, it's super cool.
Okay.
But the details of Friston's work didn't help me much so far.
We've run out of time. And as a matter of fact, besides Carl, we also had Jake Hansen a couple of weeks ago, a critique of Carl Friston's work. So we've seen all angles on that. Let me close by telling you that thank you very much for coming, so to speak, and giving your talk. And about the promise of the title, it's underestimating language or the Turing test to say that it's question answering. It's even more underestimating the robotic challenge to say that it's a matter of answering questions to a robot or by a robot, sorry. There's a lot, just as you said, there's a lot more to movement all the way to Newtonian mechanics. That's all in robotics. It's not, yeah.
Yeah, that's certainly true. I mean, I think my answer to that was very pragmatic. Like, how are we now evaluating that? I answered how we are now evaluating that in our practical work in my team. It's not an optimal way to evaluate it whatsoever, right? I mean, I proposed conceptually a while ago what I called the robot college student test, where if you could send a robot to MIT or Tsinghua University or somewhere, have it go through all the classes, write a PhD thesis, and graduate, do the defense. Like then, if the robot could really do that, like go through the university exactly the way a human does, and get a PhD, then I would be forced to consider this thing as a pretty good approximation to human level general intelligence, right? Okay. So and that's a better it's a better test than question answering. It's not a perfect one. You could still poke holes in it though, right? But it's closer.
Okay, terrific. I think we can agree on that. And thank you again for coming. I'm going to now
thanks for having me.
End the session and end the recording.
All right. Thanks, everyone. I'm going to pop off and bring my son to kindergarten. So be in touch. Bye-bye.
Moi, je fais. Ok, c'est pour 2 enregistrements. Non, pas là, ici.